So welcome back, everyone, to the Langtangen seminar. We're very happy to have Patrick Farrell today from Oxford University. Before I begin, I'd just like to note that if you have any questions, please put them in the chat so that at the end we can have a question and answer session. Just a brief introduction about Patrick. I think many people know who he is, but just in case, so Patrick is a full professor of mathematics at Oxford University, or University of Oxford, sorry. Where he's been for about 6 years or so, if I believe correctly, since 2016. No, longer than that, I guess, right? So he's been there much longer. Patrick has many accolades. I'll just mention a few. So he recently won the German Dahlquist Prize from Siam. He's also the winner of the Whitehead Prize, Wilkinson Prize, and Leslie Fox Prize. So we're very excited to also hear what Patrick has to say about his recent research and some future perspectives on scientific computing. So Patrick.
Great. Thanks very much for the kind invitation. So today, what I'd like to talk about is structure preserving discretizations in time. And my work on this has really just started with my PhD student, Boris Andrews, who's driven a lot of this. Before I say anything about the scientific content of my talk, I just wanted to say how delighted I was to receive this invitation and that the seminar series is named after Hans Petter, that he was a wonderful scientist and mentor and friend. He was extremely influential in my own career. He was a wonderful supporter, and I'm deeply grateful to him, and I really miss him a great deal. So I'm delighted to see that he's still remembered, that this is still going on. So I'm going to talk about how you discretize initial value problem differential equations in time. And these days it's not enough just to have a convergent discretization that as you put in more effort, you get closer to the right answer. As numerical analysts, as scientific computing people, we want to do this in a stylish manner. We want to do this in a structure preserving manner, that we want to think about the deep structures that our problems possess, and we want to design numerical methods that reflect and honor those. And so in the context of time, here are 4 problems that an IVP might have: symplecticity, symmetry, conservation, and dissipation. And I'll briefly mention each of these in turn. So symplecticity is a geometric property of the differential equations. If you don't know what it is, it's a little bit complicated to understand, but it's something to do with preservation of areas in phase space under the flow map. It's not quite that, but close enough. But many problems in physics possess this symplectic structure. So anything arising from Hamiltonian mechanics is symplectic, and it can be really important to preserve this on discretization. So another deep property of the laws of physics is that they often exhibit symmetries, so that they're translation invariant, rotation invariant, or if you stop the clock and you negate the momenta of every planet orbiting the sun and you reverse the direction of time, you won't be able to see any difference. The planets will continue on as they were before. So the laws of physics possess symmetries, and we'd like to have discretizations that also reflect those symmetries. And symplecticity and symmetry have been the main focus, I would say, of the subject of geometric numerical integration, structure preserving discretizations for initial value problems, as, for example, exhibited in this wonderful book, The Bible of this Field, by Geire Lübich and Vonner. There's been less work on the other two. There has been some, and indeed this text in this book about conservation laws, but there's been less focus on the last two, which are conservation laws, that the equation preserves invariance, like energy or angular momentum, and the maybe less popular sister of a conservation law, a dissipation inequality, which is that there's some special quantity, like, for example, entropy, that can only go in one direction. It can only increase or decrease at some definite rate. And what is this talk about? In today's talk, I'm going to focus on the last two, on conservation laws and dissipation inequalities. And I'm going to present a way to preserve conservation laws and dissipation inequalities on discretization, a new way to do this, in a symmetric way, without ugly, not ugly, this is recorded, without brute force methods like projections onto manifolds or Lagrange multipliers or things like this. Okay, so let me give some brief examples of what we can do that's new with the framework that I'm going to discuss. So the first thing I'd like to study is a very classical problem. I have a visiting professorship in Prague, and one of the great residents, one of the great scientific legacies of Prague was Johannes Kepler, who in 1609 told us that planets orbiting suns go approximately in conic sections in parabolae. So if you consider the two-body orbit, a planet going around the sun, and you non-dimensionalize appropriately, it has this Hamiltonian of a term of kinetic energy and potential energy, and then that induces the differential equations of motion in the usual way, where you have the time derivative of our variables, which are position and momentum, a skew-symmetric matrix, and then the gradient of the Hamiltonian. Okay, and before we discretize, let's just think about the nature of this system and what structures it possesses. So on the continuous level, this is a symplectic problem. It arises from a Hamiltonian. It also has several conservation laws. So for example, angular momentum is conserved, the energy is conserved, and there's a last one, which is less well known, but still very important, which is the Laplace-Runge lens vector. That's this LRL in the bottom right, which somehow describes the orientation of the ellipse. In particular, it's a vector that points from the sun to the point of closest approach, the perihelion. And this vector is preserved by the dynamics, and in part that's why it is shaped like an ellipse. So if you conserve these three conservation laws, you get an ellipse. Now, when we discretize, let's use a good structure-preserving method like implicit midpoint, which is a symplectic integration method, so it preserves the symplecticity of the problem. It conserves angular momentum, because angular momentum is linear or quadratic, and implicit midpoint conserves such invariance. It doesn't conserve the energy, but it does in some sense. So rather than shooting off to infinity, or as, for example, Ford Euler would, a symplectic discretization like this has an energy that oscillates around the true value of the energy for exponentially long times. So it's not conserving the energy, but it's not arbitrarily wrong either. It's getting something right. So that's why it gets an orange tick. But however, the Laplace-Runge lens vector, this invariant that describes the orientation of my ellipse, isn't linear or quadratic. It's not conserved by the discretization, and we see this in the results. So this red trajectory is the trajectory exhibited by lowest order implicit midpoint with some time step, and we see precession. We see that the orbit of our planet is rotating. Okay, let's try a different structure preserving method. So there's a method proposed by Labuda and Greenspan, which trades symplecticity, so this is no longer a symplectic discretization, for exact conservation of energy, exact up to machine precision and solver tolerances. And so now what we see is that the shape of the ellipse is correct, the shape is preserved, but still it doesn't conserve the Laplace-Runge lens vector, and the orientation isn't retained correctly. But with our approach, the approach that I will describe momentarily, we can devise a lowest order discretization, the same order as implicit midpoint and Labuda-Greenspan, at more or less the same computational cost, in fact, in this case, that trades symplecticity for the conservation of all three of these invariants, for the angular momentum, for the energy, and indeed for this Laplace-Runge lens vector describing the orientation. And hence, that's why our discrete trajectory interpolates the ellipse. At least it interpolates the ellipse at the time points that you solve for. Okay, so normally when you see a list of properties like this, the speaker is going to conclude with a flourish that his or her approach preserves all of these properties. But you notice that I've got 3 ticks but 1 X. And so the question is this the best we can do? Can we have it all? And the answer, at least in general, is no. And there's a nice theorem by Jerry Marsden and Guy Zhang, they proved it in 1988, which goes as follows: let H be a Hamiltonian which has no other conserved quantities in a given class other than functions of H, like H squared and so on. And then if you have a symplectic integrator that also conserves H exactly, it is the time advance map for the exact Hamiltonian system up to some reparameterization of time. So more or less up to some reparameterization, you've got the exact solution is your algorithm. And so while this theorem doesn't apply to the problem I was just looking at because it has more conserved quantities than a single Hamiltonian, in general, the message from this is that we have to choose between conservation or symplecticity. So you cannot, in general, hope to achieve both. And my comment here is that both properties are useful in different situations, that sometimes you may wish to preserve symplecticity of your discretization, whereas other times you may wish to preserve conservation. And maybe this is something we can discuss later. However, I don't want to give the wrong impression that the framework that I'm about to describe uh, is only for Hamiltonian problem. It extends to much more complicated problems. So for example, I'll end with an example of the compressible Navier-Stokes equations, and we can devise with this framework time-stepping schemes that conserve mass, conserve momentum, the three components of momentum. So these are, of course, globally integrated quantities, so the integrated mass, momentum, energy, but also to provably dissipate entropy with the right asymptotics. And so, for example, if we consider a scenario where entropy should be conserved in an ideal fluid, in an ideal flow, then entropy should be conserved, and this is indeed achieved with our scheme where the errors in the entropy are down at around machine precision, whereas with implicit midpoint, they're increasing by many orders of magnitude. It's not getting the right physics for the entropy. Okay, so with that motivation, let me explain how it works. And the basic idea where we're going to start is to take a variational formulation in time. Of course, Hans Petter was a big fan of variational formulations. And so just to clear up a confusion before it might start, I don't mean to solve for all time steps at once. I'm not, if you give me a difficult, expensive three-dimensional Navier-Stokes simulation, I'm not proposing to solve a four-dimensional space-time problem. We're still time stepping. You give me the solution at one time step and I'll tell you the solution at the next. And to understand this variational viewpoint, let's just first study general methods for solving a classical ODE u dot equals f of u. Okay, so here's the setup. We know the value of u equals un, at some time t equals tn, which might be the initial condition, or it might be the last time step that we've just computed. And we'd like to compute the solution at the next time step. At t equals tn plus 1, I want to know un plus 1. And here is a general picture of many, many schemes. Of course, not all schemes, but many single-step schemes, which is the following. So I'm going to consider polynomial functions on this time interval, tn to tn plus 1. I'll consider polynomials of degree s, okay, mapping into some Banach space or Hilbert space. Okay, and in order to pin down a degree s polynomial, I need to specify s plus 1 facts, right? This is a vector space of dimension s plus 1. I already have one fact to hand, which is that I know the value of this polynomial at the left endpoint, right? I want to enforce my initial condition. So that means that I need to enforce s other conditions. Okay, so I need to choose s other conditions that will determine my polynomial in this time interval, and then I'll set my next approximation to be the evaluation of whatever polynomial I've recovered at the right endpoint. Okay, and of course the different schemes will differ based on what are these s other test conditions. So for forward Euler, I'll take s equals 1, and I'll demand that the derivative of my approximation in time matches the data that I know the right-hand side of my differential equation at the test point t equals tn. Okay, so that's forward Euler. Backward Euler is very similar, except that instead of demanding that my derivative match up at the left at the start of my time interval, I'll demand that it holds at the end of my time interval. And for implicit midpoint, I'll do the same. I'll demand that the derivative matches up, except not at the start, at the end, but rather in the middle of my time interval, to which somehow you feel should be more symmetric. Okay, and of course, not all schemes use s equals 1, so lately it's become very popular to look at implicit Runge-Kutta schemes like Gauss-Legendre and so on. And so you can think of these as collocation schemes where you demand that the differential equation hold pointwise at certain specially chosen points in your time interval. However, if you want to take a variational point of view, the natural variational scheme, the natural finite element in time scheme, instead chooses another test set, which I think is very natural, which is that if I need to supply S conditions, I'll just demand that this statement holds when tested against all test functions drawn from a set of dimension of a space of dimension S. And the natural space of dimension S to use are all the polynomials of degree S minus 1, which is the time derivative of my trial space. Okay, so this is called continuous Petrov-Galerkin. It's continuous because I'm enforcing explicitly the continuity of my approximation that the polynomial at the left endpoint matches my known initial condition. And then it's Petrov-Galerkin because the space for the trial function and the space for the test function differ. The trial function is degree S polynomials, the test function is degree S minus 1 polynomials, and the difference between those being made up by the initial condition. Okay, so why is this variational viewpoint useful? Why should I want to enforce the differential equation in this variational way? It's because there's a very natural way to represent conservation laws and, as we'll see, dissipation inequalities from variational statements. So if I have a quantity that doesn't change over a time step, like for example the energy, okay, so the difference between them at the start and the end of the time interval must be 0. Well, whenever you have a difference like that, you're just itching to write it as the integral of a time derivative. And then I can apply the chain rule to write that dj dt as dj du dt. And then I have a differential equation, so I know something about u dot that's the same as f of u. And so if we put all of these things together, what we've found is a special test function, this j dash of u, that when I test the right-hand side of my equation and integrate over a time interval, I must get 0. Okay, so in other words, each conservation law has an associated test function with it. And in fact, in our scheme, in our numerical scheme, we'll represent the conservation laws with these test functions. And we'll see some examples in a moment. The same thing also holds true for dissipation inequalities. So if you have a quantity that can only increase, it can't decrease, or it might stay the same, like entropy. Okay, well, I can apply exactly the same reasoning to the right-hand side of this expression here. And now I found a special test function that when I hit the right-hand side of my differential equation, I find something that can't be negative. Okay, and so every dissipation inequality also has an associated test function with it. And so if we have a discretization described in this way, described in this variational way that the differential equation holds up to some set of test functions, if the special test function for our conservation or dissipation law is in our test set, then the conservation or dissipation behavior will be preserved, right? That's how it's going to work. The bad news is that that special test function is rarely in our test set, right? So it's rarely the case that this special test function for some complicated, non-polynomial energy functional or whatever is in fact in our test set. So what can we do? The core idea of this talk, of our work, is the following. We're going to compute discrete approximations of these special test functions. So I'll denote the approximations with a tilde on top. These approximations will be in my discrete test set. Okay, and once I have them, I'm going to modify somehow the differential equation to use this approximation on the left-hand side rather than the special test function on the right-hand side. And so it's often the case that the differential equation itself will feature terms involving this j dash of u, will replace those terms with its discrete approximation. So I'm going to go to a mixed formulation in time. I'm going to solve for extra variables. That's where the cost of this scheme will come from solving the extra variables. And then I'm going to modify the differential equation to use them. Okay, so the basic gist of what I'm about to propose is that we're going to choose some base time-stepping schemes. So in this talk, I'm only discussing CPG, finite element in time schemes, continuous finite element in time schemes, but you can modify other schemes as well, like collocation or Ragakata schemes, and so on. I'm just trying to keep it simple for the talk. We'll then identify the associated test functions for the structures to preserve. We'll introduce corresponding auxiliary variables in our formulation, discrete approximations of these associated test functions. All of these steps are mechanical, right? There's no thinking required once you know what you want to preserve. the last step is where the thinking happens. You have to modify the right-hand side of the weak formulation in order to use these associated test functions so that you can replicate your variational arguments. Okay, and we'll see how to do this by example. Usually it's quite straightforward. It's usually quite clear how to do this, but it's probably vague for now. Okay, so in order to not make it vague, let me present an example. Let's consider the Navier-Stokes equations. And in particular, I'm going to consider the three-dimensional incompressible Navier-Stokes equations. And I'm going to consider them in a thermodynamically isolated context. So I'm going to impose homogeneous Dirichlet conditions on the boundary. And I'm going to avoid having a source term so that I get dissipation of energy. And I'm going to write them in Lamb form. So this is named after Horace Lamb. So this here, the U cross vorticity, the velocity cross product of vorticity, is coming from the advection term. And then when you write the advection term in this way, you pick up the pressure changes. It becomes the Bernoulli pressure, but that doesn't matter for us. And then we have the usual viscous term and the incompressibility constraint. Okay. So these are the equations that we'll use as an example to illustrate how the framework works. So the first thing to do is to define the base discretization that we'll modify. So let's take our favorite discretization in space, think Taylor-Hood to be concrete. And then I want to get rid of the pressure because for the analysis, it's much more convenient to just work with the velocity. So I'm going to consider discretely divergence-free velocities. Okay, so I've somehow folded the pressure away by considering discretely divergence-free velocities. And then I'll take that spatial discretization and tensor it with continuous polynomials in time. And that makes my trial function space X. Okay, and then the basic discretization that I'm going to modify is that I'm going to take this equation and test it with test functions from the time derivative of this. So it's the same Taylor-Hood discretization in space, but degree S-1 polynomials in time. Okay, and so we have the time derivative on the left. We've got the advection term on the right. The pressure gradient has vanished because this X is all discretely divergence free, so that disappears. And then we have the viscous term left over. Okay, so that's the basic standard time discretization that I'm going to modify. Okay, so the next task, step B, is to identify the structures that we wish to preserve. And for this example, let's consider two. So first of all, we'll care about the dissipation of energy, so the kinetic energy. And we'll also consider the change in helicity, which maybe is less familiar than energy. So helicity is something that kind of measures the knottedness of the flow, whether the field lines of the flow, the streamlines of the flow are knotted or not. Helicity doesn't usually show up in this context of viscous incompressible fluids. It's much more studied in the ideal case in the Euler equations, because there, in fact, it's preserved by the dynamics. So it's a big deal in the topological hydrodynamics literature, sort of this picture from the book of Arnold and Kessin on that subject. It's also a much bigger deal in magnetohydrodynamics, where the helicity of a magnetic field, analogous to the helicity of a velocity field, is very important. But just to illustrate how the framework works, we'll consider this other functional, which is the L2 inner product of the velocity and the vorticity. Okay, so let's work out what are their special test functions that represent these guys. So the energy is the L2 inner product of the velocity with itself. So when we take its Fréchet derivative with respect to the velocity, that's something that eats a test function z and just gives you back the L2 inner product of the velocity and that z. And so the special test function that's the Riesz representation of that functional, the L2 Riesz representation, is just the velocity itself. And what does that mean? From the analysis that we saw before, if I want to know how the energy evolves across a time step, so EUN plus 1, the energy at the end minus the energy at the start, what it's saying is that I should test the time derivative with the velocity itself. And then we use what we know about the time derivative. So we've got the advection term and the viscous term. And here's why I wrote the 3D incompressible Navier-Stokes equations in this way, because this advection term clearly vanishes, because at every point in space, so this bracket is an L2 inner product, at every point in space, I've got something that's velocity cross something else dotted with velocity. So that has to vanish. And so all that's left is the viscous term, and this has something that can't be negative, and then a minus sign out in front. And so this is the usual energy estimate for the incompressible Navier-Stokes equations, showing that the energy must dissipate, right? The energy can only decrease. All right, what's the update law for the helicity? Well, if we work out what the Fauché derivative of this helicity function is, it's represented by the curl of the velocity, so that is the vorticity itself. So that requires an integration by parts, so it requires the boundary conditions that I assumed. And so then, since this is the special function that represents the helicity, in order to get the update of the helicity across a time step, I need to test the equations with the vorticity itself. And so then plugging in what we know about u dot, again, the same thing. For the same reasons, the advection term vanishes because this is at every point in space, the vorticity cross something dotted against the vorticity, and the cross product must be orthogonal. And so we're just left with the viscous term, which is minus 1 over the Reynolds number, the integral of the L2 inner product of the gradient of the velocity and the gradient of the vorticity. So notice here, actually, the framework is slightly more general than what I presented. I don't know what the sign of this helicity update is. It could increase or it could decrease. It depends on how this spatial inner product in the brackets evaluates. Okay? But what I do know is that if I consider the ideal situation where I send 1 over the Reynolds number to 0, then helicity will be conserved, right? So this will become a conservation law in the ideal limit. And this is what we can preserve. So the upshot of this analysis is that in order to replicate these laws discretely, the update laws for energy and helicity, we want to have approximations of the velocity and the vorticity in our discrete test space x dot, okay, the degree s-1 polynomials in time. All right, so let's do the automatic thing. It's very easy in Phoenix to introduce extra variables. So we're going to consider a mixed formulation in time, where now I'm solving for the primal velocity in x, that's the same. And then I've got these two auxiliary variables, omega-1 and omega-2. They're now living in x dot. So it's the same spatial discretization, different time discretization, 1 degree lower in time. The law for the primal velocity, this hasn't changed. It will in a moment. And then I've got these two extra equations for these two extra auxiliary variables, one defining that omega-1 is the projection of u onto the discrete test set, and omega-2 is the projection of the vorticity onto the discrete test set. So all of this is purely mechanical. But now here's where we have to think. I want to be able to replicate the energy update law discretely, right? So I want to be able to test this equation at the top with omega-1 and have the advection term disappear. That was crucial for the energy update law. And I want to have the same thing in both slots. So what that means is that wherever I see a u in this equation on the right-hand side, I should replace it with omega-1. And then that will mean that I can test this equation with omega-1 and retrieve a discrete version of the energy update law. And then if I want to recover a discrete version of the helicity update law, I want to be able to test this equation with omega-2, and I want to have the advection term disappear. So that means that I need, wherever I have this vorticity showing up in the PDE, I should replace it with the auxiliary vorticity. Okay, and so when we do that, I've underlined the terms that I've changed. Essentially, wherever I had the velocity, I now use the auxiliary velocity. Wherever I had the vorticity, I now use the auxiliary vorticity. And here is my final time discretization. Okay, and now I hope that I show that I can replicate these energy and helicity update laws. So I'm just going to retrieve two of the equations from the three in our final time discretization, the two that are relevant to us. So we know from before that in order to get the energy update, I need to test the equation with the velocity itself, okay? But then by the second equation, the auxiliary equation that I've introduced, this is the same as testing with the first auxiliary variable, omega-1, because u dot is a valid choice for V1 here. So that means that I can test this equation with omega 1. And then so using this equation, I can expand it like this. And then for the exact same reasons as before, this advection term must vanish. And I'm left with the discrete version of the energy update law. It's not exactly the same. Instead of having U here, it has my auxiliary approximation to U. But the structure of it is the same, that I have something that's definitely not positive and with the right asymptotics. So if I consider the ideal limit as the Reynolds number, as one over the Reynolds number goes to 0, we recover a conservation. Similarly, for the helicity, if I consider the same kind of analysis, here I pull out two equations from the final time discretization, the two relevant ones. If I want to get the update law for helicity, then I test with the vorticity. From the second equation, that's the same thing as testing with the auxiliary vorticity. And then expanding from the first equation for the exact same reasons as before, the advection term will disappear, and I'm left with something that looks an awful lot like the original continuous helicity update law. Okay, and so again, with the right asymptotics, in the ideal limit, we recover a conservation. Okay, so this all looks expensive. I'm introducing all of these extra variables. Do I always need them? And the answer is no. Some of the time you can get rid of them, and we know when. And more or less, it's when, if you know the primal variables, can you explicitly compute the auxiliary variables. So in this case, the auxiliary velocity is the same spatial approximation, just discretized in time with one lower degree, and in the right basis, that's just throwing away one coefficient in your expansion. And so you can compute the auxiliary velocity explicitly from the primal one, so you don't actually need to compute it and store it. The auxiliary vorticity, however, you do need to compute. Okay, and what we've just done, what we've just been through, I hope it wasn't too traumatic for you, is an arbitrary order generalization of a scheme that was already known in the literature at lowest order. So Rebholz had proposed this energy and helicity conserving finite element scheme for the Navier-Stokes equations at sort of implicit midpoint level of discretization, whereas this viewpoint or this re-derivation shows us how to do this at arbitrary order. Okay, but it's not just that we can get higher order versions of known schemes, because we now understand how to impose these conservation and dissipation laws in a nicer way. We can apply them to problems that were previously intractable from the point of view of doing it by hand. Okay, so if we consider the compressible Navier-Stokes equations, which is a much more difficult beast to discretize, I won't go through the same level of detail, don't worry, but we agreed to preserve four structures: mass conservation, momentum conservation, energy conservation, and entropy dissipation. And you can do it in exactly the same way. So what you do is you figure out what are the special test functions for each of these four quantities. You introduce auxiliary variables for those special test functions. Some of them you can eliminate, some of them you don't need to solve for, other ones you do need to solve for. And then you modify the equations that wherever you saw the primal version, you replace it with the auxiliary one. And so just to give you a flavor of what it looks like, for mass conservation, the test functions are pretty straightforward. It's that the density test function is 1 and the others are 0. And so our scheme is globally mass conservative. Now that's not an enormous surprise. You kind of have to break a time-stepping scheme in order to not achieve this. Much harder is energy conservation, because the energy in the compressible Navier-Stokes equations is not quadratic. So it isn't preserved automatically by, for example, Gauss-Legendre implicit midpoint type schemes, because it's 2 of the velocity, it's the velocity squared, and the density. So that's why it's not quadratic. And so here, the test function for energy conservation is temperature test function 1 and velocity test function itself, velocity itself. And so we achieve up to machine precision and solver tolerances, exact conservation of the total energy as it trades off between kinetic and internal energy. And that's not at all trivial to do. And for entropy dissipation, it turns out to be quite interesting. The special test functions that you want turn out to be quite thermodynamically significant. the test function for density is G, where minus G is the Gibbs free energy per unit mass per unit temperature. So something of substantial thermodynamic significance. We just worked this out. We didn't know that this would be the answer ahead of time. I'm sure if I knew more thermodynamics, I would have predicted this in advance. And the special test function for the temperature is 1 over the temperature. Of course, also something that shows up a great deal in thermodynamics. And so here is a not very exciting picture of the entropy increasing and not decreasing in a simulation. Okay? But what's important here is not only are we guaranteeing that you get the right physical behavior, that the entropy cannot decrease, we also do it with the right asymptotics. So in the ideal limit, you get a conservation law for entropy. And here's an example of a simulation that we've done. It's not incredibly impressive, but it's not entirely trivial either. So we've got a two-dimensional domain with periodic boundary conditions in order to make it thermodynamically isolated. I start off with a uniform density and a uniform temperature, but I initialize with a supersonic perturbation in the velocity going to the right. And then as time advances, the fluid propagates to the right in a supersonic manner, and you get these shock waves, this discontinuity in the temperature and the density. And eventually it goes to the right and then starts catching up with itself. And so you get sort of an interaction between the front of the shock wave and the back. So it's not entirely trivial. And yet throughout all of this, the energy is conserved, the entropy is dissipated with the right asymptotics. Okay, so let me show one recent application of this idea where I think it's really essential to get the physics right. And that's in the Parker problem, where structure preservation isn't just a nice to have, but is really important for getting any reasonable numerical simulations out. So let's consider ideal magnetohydrodynamics, or at least magnetically ideal magnetohydrodynamics. So we are solving for the flow of a conducting fluid. We've got a velocity, a pressure, a magnetic field B, and an electric field E. We have a viscous term in the fluid, so the fluid is not ideal, but there's no resistivity, so the magnetic component is ideal. And this system, of course, systems like this can be used to describe many, many features. Most of the matter in the universe is in the form of a plasma. Things like the magnetic field that's generated by the motion of the outer core in our planet, or what's happening inside the sun, or what happens in a fusion reactor, will be described by equations related to these, maybe not exactly the same. So for this system of PDEs, there are two structures that we want to preserve. So the first is that the energy is dissipative. This is a dissipative system, but there is something that's conserved, which is the helicity. And in this case, it's the magnetic helicity, which is, you can write as the L2 inner product of A and B, where A is any magnetic potential. So any vector field such that curl A is the magnetic field. And this helicity is conserved because it's magnetically ideal. Okay, and in 1972, there was a conjecture made by a very, very famous astrophysicist called Eugene Parker, which says the following: for almost all initial conditions, the magnetic field develops tangential discontinuities during ideal magnetic relaxation, during undergoing the solution of this PDE to a force-free equilibrium, to a stationary state. Okay? And so this guy Parker is very, very important. So he conjectured the existence of the solar wind. For example, the shape of the magnetic field in the outer solar system is now called a Parker spiral. You might have heard of the Parker probe that NASA have in orbit around the sun. And the reason why Parker was thinking about this was because he was thinking about the coronal heating problem. It turns out that the corona of the sun is millions of degrees hotter than the surface of the sun. And what is the thermodynamic mechanism that transmits all of this energy into the corona from the sun itself? And one of the main theories proposed by Parker is to do with this magnetic relaxation. So the idea is that when you develop these tangential discontinuities, there's high magnetic stress, and this is relieved in real life. Of course, in real life, it's not magnetically ideal. And then what happens is that you get a reconnection event, and this is acts like a nanoflare and transmits energy into the corona. So that's why he was considering this problem. And why did we mention the helicity? The reason is that there's a crucial relationship between the helicity and the energy. So the helicity provides a lower bound up to a constant on the magnetic component of the energy in the magnetic field. So this means that while the system is dissipative, the dynamics are dissipative, if you start with something that's topologically twisted at the beginning, if you have non-zero helicity, so knotted field lines in your magnetic field, you cannot relax to the zero state because this helicity is conserved and is non-zero. So in other words, the energy in your magnetic field cannot decay to zero. So the helicity is providing a topological barrier that's crucial for the physics of this problem, right? If you don't preserve the helicity, and if you don't preserve a discrete version of this Arnold inequality, you won't get the right answer. You won't get any reasonable numerical simulations. So what did we do? Well, we considered a much simpler system of PDEs called the magnetofrictional equations, where we retain the electromagnetics parts, but we make an ansatz for the velocity field. So we're not solving an equation for the velocity field. There's not a momentum balance anymore. It's just an explicit function of the magnetic field itself. But the reason why this is a nice system to look at is because, well, it's simpler, but it has the same structure. So it dissipates energy, it conserves helicity, it satisfies the Arnold inequality, and it has the same equilibria as the original MHD system. So, and since the Parker conjecture is a conjecture about equilibria, it's perfectly reasonable to study the equilibria of this magnetofrictional system instead. Okay, and so what we did was we devised a structure-preserving discretization of these equations. And this requires, I don't have time to talk about it, but it requires both the ideas in this talk about how you discretize in time, but also combined with finite element exterior calculus. In order to make sure that there's a discrete helicity at all, you need to make sure that your magnetic field is exactly divergence-free. And so this was work with Kaibo Hu and my PhD student Ming Donghe. So if you apply a naive discretization, then what happens is that you start off with something that has non-zero helicity. The helicity isn't conserved, so it decays to zero, and then the energy decays to zero also, very, very quickly, and you get something that is just zero when, of course, it shouldn't be. But if you use a discretization like ours, which is structure preserving, the helicity is conserved, so this blue bar is going straight across, and there's a discrete version of the Arnold inequality enforced so that the energy is up to a constant, lower bounded by this helicity, and so that's why you relax to a state that has non-zero energy. So this topological barrier is preserved. And so we've been running some simulations on Archer 2, the UK national supercomputer. So these are visualizations of the magnetic field lines colored by the strength of the magnetic field at the start and at the end of a long simulation. And you see, if you don't do this, then it just decays, all decays to zero. But here, the knottedness of these magnetic field lines has been preserved. And so it prevents the decay of the field to zero. Okay, so let me conclude. We can now, with work, you have to think on a case-by-case basis, but with work, we can discretely replicate many conservation and dissipation laws. And I think this has lots of potential applications in designing schemes for problems with these structures. So in magnetohydrodynamics, in multi-component flows, that's something I'm working on a lot these days, where you've got more than one chemical species in a mixture, viscoelastic fluids. The PDEs arising in geometry are usually written down precisely in order to dissipate something. Hamiltonian systems, maybe with infinite numbers of conservation laws. Of course, we can't preserve infinite numbers, but we can preserve some. The Lorentz system for a charged particle in electromagnetic fields is something very interesting. Gradient flows, and many, many more. And with that, I'd like to conclude, but I do have one relevant announcement to this seminar before we go on, which is that I'm on the prize committee for the Langtangen Prize, which isn't run by Simula, but is run by close friends of Simula. So the Langtangen Prize has just been established. We're going to make our first award this year, and it's awarded to the best paper published in a given calendar year on the foundations of numerical simulation technology. And the award of $3,000 every year is kindly supported by the Ridgway Scott Foundation. And so nominations for this year have closed. They closed on the 1st of April, but by all means for next year, please submit nominations for the Langtangen Prize. So thanks very much.
So thank you very much, Patrick, for this beautiful presentation. I will give the floor to Marie, who's going to either ask her own questions or the questions from the audience.
Thank you, Thomas, and thank you so very much, Patrick. This was very intriguing and very pedagogical talk as well. Thank you so very much. I'm looking forward to discussing this more with you at various levels in the future. So I have a few questions listed here. Okay, so the let's see what I found here. So I think I'll start with a question on my own that popped up, and I think that maybe you hinted at this in connection with the Parker problem. So I wanted to ask about the interplay between errors in space and time here. Because in a way you seem to have isolated very much any error or any problematic data that might appear from the spatial discretization, and kind of isolated just the temporal discretization. I was wondering, maybe you could comment a bit more on this, whether there's any devil in the details here.
To some extent. So for the most part, what I've presented is independent of spatial discretization. So if you go back to the incompressible Navier Stokes example, it really doesn't matter to me if you use Taylor-Hood or if you use a HDFL2 discretization or if you use Scott-Vigilius or something like this, right? So in that sense, that doesn't matter. In the Parker problem, the reason why it was important is that in order to define the helicity, you need to have a magnetic potential. So it was the L2 inner product of the magnetic potential and the magnetic field. But that, is of course closely related to Hodge decompositions, and you can only guarantee the existence of such a magnetic potential if your magnetic field is exactly divergence-free, right? Not just discretely divergence-free with respect to some chosen space of Lagrange multipliers. And that was where the coupling between the finite element exterior calculus and the discretization. But for the most part, I would say that this idea is separate. And I guess really it's because we're considering the time evolution of globally integrated quantities. So, this is because it's a narrow class of structures that we want to preserve, we can forget about the spatial discretization for the most part.
So a follow-up question on that. So for instance, you're guaranteeing dissipation of some sort, for instance. Can you say anything more about that in, for instance, a rate of dissipation or?
Indeed, yeah. So that's really crucial, and maybe I didn't highlight it well. So if you go back to the let's consider first the continuous energy law.
Yeah.
So it looks like minus 1 over Reynolds number integral in time gradient squared, right? If you go to the discrete energy law that we derive, it looks very, very similar. It's minus 1 over the Reynolds number integral in time gradient squared, except that instead of the primal velocity, the one that you're solving for, it's this auxiliary velocity. So long as your discretization in time is reasonable enough that if you lose one order lower, that omega-1 still looks something like U, then you expect this to be a good approximation for the energy update law. It has the right structure, it has the right sign, it has the right asymptotics with Reynolds number, but as a discrete approximation, you could think of cases where you could rig cases where omega-1 is a poor approximation of U, and so your energy law will be wrong, right, for that time discretization. But if you have a reasonable time discretization, then you expect this to be close.
Thank you. There's another question here. So you hinted at that it may be sometimes advantageous to preserve simplicity and sometimes advantageous for conservation. Could you elaborate on this?
Sure. So I think this is something where my thoughts are still evolving, or our thoughts are still evolving. But I can show one example, not immediately because I don't have it in this presentation. But if you consider the Benjamin-Bohner-Mahoney equations, so this is an example that we study in the manuscript. This is a Hamiltonian PDE, so it has a symplectic structure, and it also has 3 conservation laws. And if you apply, a good structure-preserving discretization, so a not lowest order Gauss-Legendre scheme, by, let's say for a given setup, by time equals 10,000, the discrete solution just looks completely wrong. But if you apply a conservative discretization, the solution looks just right. It's slightly shifted, it's slightly translated because of approximation error, but it's qualitatively got the right features of the wave. And so my current thinking, which is subject to update and renewal, is that symplecticity is really a property of applying the flow map, solving the differential equation for many, many different initial conditions. And my suggestion at the moment, my tentative suggestion, is that if you're doing something like that, where let's say you're solving an SDE or something where you're going to draw many samples and you're going to solve the differential equation many, many times, symplecticity is probably the more important property. But if you want to solve the differential equation once and physical fidelity is the more important thing that you're worried about, then at least my current numerical experience is that preserving conservation laws is more important. But that's necessarily tentative, and I'm sure people will disagree.
Okay, thank you. So we've also asked all of the speakers that we've invited to this spring's Langtangen seminar to maybe share some thoughts on what they think are the most important ideas from their point of view on the future of scientific computing. Would you like to share some thoughts?
Sure. Well, so I guess my interpretation of the question was slightly different, which was kind of making predictions, which is a much more dangerous game than I think than the one you just outlined. But that's the one I prepared, so that's the one we'll go for if that's okay. And so here are my current thoughts. Predicting the future is hard, but over the next 10 years, I expect to see in the numerical solution of differential equations, I expect to see more thermodynamics, more pure mathematics, more variational inequalities, and more data. And I'll expand on each of these points in turn. So my impression, having done this for a little while, not as long as others, is that in scientific computing with PDEs, we often study simplified problems, right? And of course, this is the right thing to do. If you have a new way to discretize something, you first study the Poisson equation. That's of course natural. But the models that we often turn to again and again and again aren't thermodynamically satisfactory. And I talked about one today, right? The incompressible Navier-Stokes equation. So if you take an incompressible fluid, it's undergoing viscous dissipation, but because I've thrown away the energy equation in the equations that I studied earlier, there's nowhere for that heat to go, right? So that's why we get energy dissipation. It's not conservation of energy, it's energy dissipation. But if we did have a temperature, if we were carrying around a temperature, it would cause the fluid to heat up. But the Gibbs relation from thermodynamics tells you the following, that if your constitutive relations, so your density and internal energy, are independent of pressure, the density must also be independent of temperature. And so that's a consequence of thermodynamics. And so what that means is that for an incompressible fluid, hot fluid cannot rise. So, and of course there are workarounds like the Boussinesq equations, but these aren't thermodynamically satisfactory. And so I think that over the next 10 years, we'll see research focus more on real thermodynamically consistent problems and less on simplified ones, in part because our algorithms are better, in part because we have the computing power to tackle more realistic problems. Another remark of where I think the field is going is I think that we're going to see more pure mathematics. And of course, we're already seeing a great deal of this. So when I was a PhD student, longer ago than I care to admit, I didn't have any idea what cohomology was. And I should have done if I was paying attention to the literature, because finite element exterior calculus was starting then. But now I use these ideas every day. There's not a single workday that goes by where these ideas don't impinge. So that's an example where what I would call pure mathematics is coming into our field. I'll also mention some things that really excite me of what I've seen going around lately. So another example of how ideas from pure mathematics are revolutionizing scientific computing is the work done by Ewan Spence and Jeffrey Galkovsky on using microlocal analysis for Helmholtz, right? So they really seem to be able to understand the numerical solution of the Helmholtz equation, much better than we could before by taking ideas from the pure analysis of these types of problems. And I'm really intrigued to see over the next 10 years what ideas can group theory or representation theory or algebra, many other fields, bring to solving PDEs. So Sheehan Alber, for example, is doing really exciting work in this direction using representation theory to build spectral bases for equations so that exhibit some kind of decomposition, right? So that you can break it down into a block diagonal matrix at the end of the day. And it could be from, I think this is something that's only going to increase, and I think it could be from areas of pure maths that I haven't even heard of or I don't think about very much. Another prediction is that over these years, I think we'll see more variational inequalities. So again, as an undergrad, I absorbed the idea that, we write down the laws of physics as PDEs, that PDEs are God's language for writing down the universe, and I had never heard of variational inequalities. But actually, it's very, very hard not to be in contact, right? From conception in the womb until death in our beds, we're in contact with something. And that means that in order to describe our displacement, we should be writing down variational inequalities. And I think that VIs are vastly understudied. If you sort of look at the ratio of numerical study to scientific importance, I think, of course, many, many people have studied VIs, but I think the denominator is so large that makes this ratio very low. And I think part of the reason is the mathematical difficulty. They're just much harder, non-smooth, non-linear than PDEs. And part of the reason is that traditional algorithms that we've had to date have been mesh dependent. So it's been much harder to solve big instances of variational inequalities. And I think some of the work going on at Simula with the latent variable proximal point could really change the game here, that maybe if we're able to solve bigger variational inequalities in mesh independent ways, that people will be more likely to use VIs to model situations that should be modeled with VIs. And then, well, more data. I mean, I guess every speaker is going to talk about this. It's obvious to everybody that data science is changing our world, right? And as other speakers have pointed out, and no doubt will point out in the future, I won't elaborate too much, there's a natural synergy between numerical simulation of physical laws and data-centric approaches. So we need data, right, for constitutive relations, initial boundary conditions. Data-centric approaches need physics-based predictions and training data. And I think the most immediate place where we'll see data science change the practice of solving PDEs is in reduced order models, right? So linear approaches like I'm going to build some subspace and I'm going to project my equations onto that subspace in order to build my reduced order model are very good for linear problems, but they just don't appear natural for real world nonlinear ones, right? And so I think that taking nonlinear approximations with neural networks seems like a much more natural idea. And so I expect that in 2035, every PDE solver will come with neural network-based reduced order models for multi-query problems. When you're doing PDE constrained optimization or uncertainty quantification, you'll use both data science-based reduced order models along with the full fidelity PDE solver in clever ways in order to achieve the goal that you're aiming for. Okay, and so to make some predictions, some things I think won't change. Newton's method will remain the default technique to deal with nonlinearities. That's been true since the 1670s or so, and I expect it'll be true for another 10 years. We'll not routinely be using quantum computers, is what I expect. The laws of physics will still be important, so it will still matter to solve them numerically. PDEs, I don't think, are going away. The traditional PDE solution techniques, like the finite element methods, will still outcompete neural network-based alternatives for solving PDEs, not considering data assimilation or inverse problems or anything like that, but just for the pure task of solving PDEs. I think that's the case today, and I think that'll be the case in 10 years' time. I think that neural network-based approaches will outcompete traditional techniques like POD for reduced order model construction. and that these reduced order models will primarily be constructed using numerical solvers rather than experimental and observational data, just because it's so much easier to solve a PDE on a computer than to go out and do an experiment or to measure things accurately. And so that's what I'd like to say there.
Thank you so very much, Patrick. This was above and beyond what was expected, and I would love to continue this discussion. There was a hand raised, and we're not accepting questions from the audience, but please do post it in the chat if you can. There's about -0 minutes left, so I think I would like to give the word back to Thomas, because maybe you have a few questions that you're dying to ask Thomas, and maybe a few extra minutes.
More of a technical question that is probably not appropriate after this this is interesting set of predictions. But I was just curious about something you said at the very end, where you said gradient flows can somehow be treated with this this new technique. Could you elaborate on that? Because gradient flows are very important for optimization.
It's not something I've investigated in great deal. I think it's I mentioned that because you're designing differential equations to dissipate something, and so dissipating something at the right rate seems to be important. But I haven't done any work on any examples. I haven't got any compelling cases where my framework gives you a better discretization than what you could do before. So this is still very much tentative future work.
Right. Okay. Thank you. Okay, so I would say now, yeah, they're at -1 minute. So let's thank. Oh, wait, Marie has another question.
Yes, I just wanted to make one comment for 1 minute. I could comment on many of your predictions, Patrick, but I wanted to say that I completely support the idea that the interplay between different branches of pure mathematics and applied mathematics, I think, will be important. And it's also very interesting and inspirational. And that requires interaction arenas, right? I think. And I think that will be an important part to think about.
Yeah, that's a really good point. Where do we find these people, and how do we meet them? How do we learn what they're doing? How do we build a common language? These are all difficult social challenges.
Thank you.
Great. So once again, I'd like to thank everyone for coming. I'd like to thank Patrick once again for this this wonderful talk and discussion, and I look forward to seeing you all next week. So thank you.
Thanks very much.